continue worksheet 16B. For part B here, deflection of the free end with the load as shown. And we need to go to use appendix D again to find out the superposition. So we have that is cantilever. And cantilever for this appendix D is only the first three finger, as you can see. Distribute concentrated load P for the finger 1, distributed load for the full length of the cantilever, and the couple at the end. Let's see our problem, is there anything close to? It seems not really. Everyone see that? Nothing that we have distributed load in appendix D, but it go through the whole beam, not only part of that. Go back here. So how can we do that with the superposition given the requirement to apply that we showed earlier in the lesson? Have to be exactly the same finger, right? But here you see the finger number 2, the distribution, the distributed load, it go through all of the length of the cantilever. Of course, we can eliminate the finger 1, which is concentrated load, and finger 3, which is the couple for the cantilever here. So how can we deal with that here? And now I show you this. Okay, so let only have only the distributed load. So what should be the behavior for this load as it applies? So let's write down here. We can have that with that load with the cantilever. Then we have the beam going. Okay, so if something like this, the load, assume if there is no 4 meter at the end, and only the distributor throughout for 6 meter. And that load is 6 kilonewton per meter. And as you can see, if the problem like this, then we can apply from finger 2 directly. Finger 2 here directly. Unfortunately, the problem is not that way. So if even the problem, yes, so what should be the elastic curve? As you can see, it will be slope start at 0 at the fixed support, and then it start going down here with the curve like that. And what happened if we stick another 4 meter onto this beam at the problem given? So another 4 meter. If we have another 4 meter at the problem with us here, so what we can say about the beam, if we just attach that 6 meter cantilever another 4 meter, then and no load apply, then as you can see, if you just stack it to the second component, they just go straight, right? It just goes, I put another color, just go straight. Make sure I draw it straight in here. Draw straight. So it's straight. And I exaggerate for that one. Go down there. It's straight. So if we find out the deflection at free end, which is this is the deflection we want to find out. This is the deflection we want to find out. That free end of the total cantilever 6 meter length. But from the finger 1, I can be able to find out that deflections. If I can be able to find out this deflection y2, then we add those two, we can have the deflection y, the question asked, okay? And of course, as you can see, when you don't have the load in the 4 meter, the slope starting, it will be, the slope, it will be constant throughout that 4 meter. What does that mean? If we find out the slope at the endpoint of 6 meter, that is theta, then it will be theta for the whole 4 meter. theta for the whole 4 meter. Everyone see that there. So what does that mean? If we zoom in this portion, if we zoom in this portion, these triangles, and let's write down here, triangle we have here, and we have the elastic curve, and we have the line there, and as you can see that is slope theta at that point, and we have 4 meter here, and that is y2 as you see from that. So for small deflection, and we already know the tangent about equal to the angle of the slope theta if it's small deflection. So with that we can have, with that point here, zoom from that, we have apply to this if it's small deflection, then for small deflection, what do we have? Then the tangent theta equal to theta in radians, and apply that tangent in this case opposite over adjacent. So you have that theta about y2 opposite about the over the adjacent 4 meter. So what does that mean? We can have y2 equal for theta. What is theta? Slope at the end of the cantilever 6 meter, as you can see there. So what that here for this problem now, it become y, the slope at 10 meter cantilever free end, it equal to y1 for the cantilever of 6 meter at the end 6 meter, y1 plus y2. And from that, as you can see, y2 equal to 4 theta, right? So the slope for the 6 meter. So in this case, we only use the finger with L equal to 6 meter. And with that, we can find out the finger number 2, and we find out the maximum deflection at 6 meter, which is y1 equal to negative WL4 over 8 EI. And then slope at n, negative WL cube over 6 EI, and we time the length 4 meter, we will get the total deflection for the beam, the cantilever of 10 meter. So again, for this equation, we only apply the cantilever for the 6 meter, and then not L equal to 10 meter, because the W only apply for the whole cantilever for the finger here. And with that, we can go back here and write the equation I just said. So y equal to the maximum deflection at 6 meters, which is W L 4 over 8 EI from finger 2, and then negative, in this case, y2 equal to 4 theta. So we have 4 slope, theta is slope, which is equal to that slope at n, negative WL cube over 6 EI. So plug here, we can have WL cube over 6 EI. And everything L, again, keep in mind that is 6 meter, not 10 meter. So you have that equal to, plug in negative 6 kilonewton per meter, L equal to 6 power 4 over 8, 200 E, 200 times power 6 kilopascal, and then area moment of inertia should be in mid power 4, so 10 negative 6, and then negative 4 W 6 L, again 6, not 4, not 10, 6 3 6 200 10 power 6, and then 410. Negative power 6. And that whole thing. From that, we find out the deflection equal to 0.0224 meter negative. So what does that mean? It equal to y max, y at free end equal to 0.0224 meter going down. And that's the answer for the part B, and we will continue for the part C in the next.